So now let's look at some trig integrals that look quite simple, but they're not as simple as, they're not that straightforward. They're actually easy, but not straightforward. Let's put it that way. The first one is the integral of tangent of x dx. I think we tried this in class. The trick is to rewrite it as the integral of sine of x over the cosine of x. And we know that sine of x over cosine of x is equal to tangent of x. So this will allow us to use u substitution. If we let u be cosine of x, now this means that du dx is equal to negative sine of x, and dx, how about, let's bring this a little closer so that everything will fit nicely on one line. So if that's the case, then dx or du, let's do du is just gonna be negative sine of x dx. All right, so we come to our original integral. So sine of x dx becomes negative du, all right? Because du is negative sine of x dx. So if you look at this as 1 over, let's write it as 1 over cosine x times sine of x dx, okay? Then that means that this is 1 over u times negative du. We can factor out the negative, and let's go one by one. And this is the same as natural log of the absolute value of u plus c. However, u was cosine of x, so this is minus natural log of the absolute value of cosine of x plus c. This is perfectly okay, but we can write it as natural log of the cosine of x to the power of negative 1/2, right, plus c. And cosine of x to the power of negative 1/2 is the same thing as 1 over absolute value of cosine of x, which we can definitely write as natural log of the secant of x, because 1 over the cosine of x is the secant of x. All right, so that's the integral of tangent of x, integral tan x dx. Now, let's try another problem. Let's try the integral of secant of x dx. This is not quite easy to see, but I will show you the trick. Let's look at this as a secant of x times a fraction. Now that fraction is something you may not expect, but when I do it, it's going to make sense to you. I'm going to multiply this by 1, multiply secant of x by 1, but I'll write 1 as secant of x plus tangent of x over secant of x plus tangent of x. This is definitely 1. Now, what I can do is expand. If I expand the numerator, I get secant squared of x plus secant x tangent x all over secant of x plus tangent of x. So I'm doing this. If you're good with your derivatives, it's gonna become a little clearer in like a second while I'm doing this. Why I'm doing this? Because if you look at this, if you let u be equal to secant x plus tangent x, then the derivative of u du dx the derivative of secant of x is definitely secant of x tangent of x, and the derivative of tangent of x is secant squared of x. So this means that du can be written as, if I want to write the secant squared of x first, if that's okay, secant squared x plus secant of x tangent of x, cross multiply, I put dx here. Okay, so this will definitely allow us write the numerator, which is secant squared of x plus secant x tangent x dx. We can just put du there, so we just have du all over u. So this rings the bell. This is just the same thing as 1 over u du, which we're familiar with. I didn't even need to rewrite it this way. I'm just, for the sake of being too clear. But this is du over u is the same thing as 1 over u du. And we've done this several times. So this is the natural log of the absolute value of u plus c. So this is the same thing as natural log of secant of x plus tangent of x. Okay. All right. So the other integrals I want us to look at are the integral of cotangent of x dx. Okay, so I'm not going to spend too much time on this, but the trick is to rewrite it as cosine of x over sine of x dx, and then do the same kind of trick. If you let u be sine x, in this case you end up with an answer that is natural log of sine of x plus c. So here you're gonna let u equals sine x and do the whole thing. Look for du, replace dx with du times something. All right, and then number 4, I would want you to try also cosecant of x dx. So the trick now is similar to that of secant of x. So you're gonna have cosecant of x. You're gonna have it as cosecant of x and then multiply it by 1, but we're gonna write 1 as cosecant of x plus cosecant of x cotangent of x all over cosecant of x plus cotangent of x. And then you let u be equal to cosecant of x plus cotangent of x. All right, so if you do this right, I want you to pause and try this yourself, but I'm going to write the answer and then you can come back and check if you got the same answer. All right, so pause and then come back. Now you're back. So this is the answer I got. I want you to check this answer because I did it really quickly. So you might figure out I made a mistake, but I'm not sure. I'm sure I didn't make any mistake because I'm always right. No, I'm not always right. I make a lot of mistakes. Okay, so those are the 4 integrals. So let's summarize. We need these four new integrals. We know that. Let's summarize. Let's say summary of basic trig integrals. Basic trig integrals. We're not basic at all, but some of our integrals are basic. So, first one, the integral of sine of x or of cosine of x. This is the easiest. This is sine of x plus c. And then the integral of, make it 2 here. The integral sine x dx is equal to negative cosine of x plus c. All right, so we know that from way back when, but the new things that we're learning today is that the integral of tangent of x dx is the same thing as the natural log of, let's see, what did we get? Let's go back here. I'm thinking of which one to write. I know we had like a lot of answers, but which one did we choose? We chose, I'm going to write negative. I'm going to write negative natural log of cosine of x plus c. Now, I want to squish this a little bit just to give me some space. All right. To write other things, other beautiful things. Okay. So, and I'm gonna do the same thing right here. Nice. All right. So, how about we look at the integral of cotangent? Whoa. No. 4. Integral cotangent of x is the same thing as let's see, what do we have? We had natural log of sine x plus c. You know what? I want to put all the cos on one side. So maybe that won't work out at the end, but who knows? Let's just do it like that for now. This is number 2. Call that number 2. Oh no, what am I doing? I'm just messing things up. Okay. All right. And we're going to make this number 1. Come here. This is number 1. Okay. Well, I just want to separate my numbers because they look like they're multiplying these integrals, and that's not my intention at all. On the 1 here, and then I'm going to call this number 2, and then number 3. Then call this number 4. All right, let's do number 5. The integral of, let's do secant of x dx. This is natural log. Oh. Well, natural log of secant of x plus tangent of x plus some c. And then number 6, the integral of cosecant of x dx. I'm going to come down here and I'm going to write it. It's negative natural log of cosecant of x plus cotangent of x plus c. Okay. So I call them basic, but maybe only the first two is actually basic, but let's just leave the word basic there. These are really good to know. They're good to remember. I encourage you to remember them. Okay, so let's look at another class of integrals. How do we integrate things that look like this? Integrals that look like this. Tangent to the power of mx, tangent mx, secant x to the power of n dx. All right, so there's a rule. If you remember, in the last lecture we looked at how to integrate sine x to the power of m, cosine x to the power of n. So there's a similar rule here, but it's not quite the same. So just learn this one. So the rule is, if the power of secant, well, power of secant in this case is n. So if n is even, what do? You factor out a secant squared x, factor out a secant squared x, right? What else do? You rewrite the remaining terms or remaining factor, but let me just remaining term remaining factor in terms of tangent of x, and then you let u be equal to tangent of x and apply u sub. All right, okay. Now, how about a situation where m is odd? So if the power of tangent is odd, if m is odd, what you do is you factor out a secant x, tangent x, and then you rewrite the remaining factor in terms of secant x. And then what do? You let u equal secant of x and you use u substitution, u sub. Okay, this doesn't cover every case, so how about when both of them are even or when both of them are odd? Well, if both of them are odd, then you can use case B. But if both of them are even, you can use both of them are even, you can use case A. But how about if it switches? If M is odd, sorry, if M is even, but N is odd. So in that case, you're kind of on your own. You have to figure out what to do. You have to do more manipulations. All right. So let's look at some examples. Example 1. Examples number 1. Let's try to evaluate tan of x to the power of 6, secant of x to the power of 4 dx. All right. So in this case, n is even. So the power of secant is even. So what do? We factor out a secant squared x. So we're left with secant squared x dx. And if you remember from when we dealt with cosine and sine, we were able to save, or we needed to save whatever we factor out, because it's going to help us with u substitution. Now, what we can do is to rewrite, or what we should do is to rewrite everything remaining in terms of tangent. And what does that mean? That means that secant squared x, we have to, this secant squared x, the green secant squared x, we need to rewrite it in terms of tangent of x. Now, if you think back to the previous lecture, we looked at several trig identities, and one of them was that tangent squared x plus 1 is secant squared x. All right, so we can go back, or we can go here now, and instead of secant squared x, we just put tangent squared x plus 1 there, and we still save this. All right, so now you can expand. You have tangent to the power of 8x plus tangent to the power of 6x, and then you have secant squared x dx. U substitution. You now let u be tangent of x, because you have its derivative sitting out here, secant squared of x. So that means that du dx is secant squared of x, so that du is just secant squared of x dx. And we have secant squared of x dx right here. So we can just go ahead and replace it with du, and everything will be in terms of u, and then we can happily integrate. So this is u to the power of 6 plus u to the power of 8 plus u to the power of 6 du. All right, so that's u to the power of 9 over 9 plus u to the power of 7 over 7 plus c. So this is tangent 9x over 9 plus tangent 7 over 7 plus c. Okay. All right. Now, how about we try another one? Let's try I'm gonna do this one. How about tangent to the power of 5 Let's use y. Y secant to the power of 7 y dy. All right, so at least here we have one of them is both of them are odd, so that means we can use the case when m is odd, when the power of tangent is odd. So we have to factor out a secant x tangent x and rewrite the remaining in terms of secant. So that's a good thing. So we can go ahead and factor out secant y, tangent y. So we're left with tangent to the power of 4y, secant to the power of 6y. And then we factor out secant y, tangent y, dy. And we save this. We save this. We save this. So our goal now is to rewrite everything, whatever is remaining over here. This remainder, we have to write it in terms of secant. All right, because we have the derivative of secant, which is secant y tangent y. Sit now there. All right, this might not be very straightforward. It's straightforward. It just requires more work than usual. What am I trying to do here? All right, tangent to the power of 4 can be written as tangent squared y squared, secant to the power of 6y, secant y, tangent y, dy. So then we can write tangent y squared as secant squared y minus 1 squared. That should be obvious by now. And then we have secant y, tangent y, dy. Remember, this is what we're saving. Okay, now we expand. If you expand this, you get secant to the power of 4y minus 2 secant squared y plus 1, and then you're multiplying it by secant to the power of 6y. Okay, and then you're saving your secant y, tangent y, dy. You're saving this. Now what can you do? You can go ahead and expand. You have secant to the power of 10y minus 2 secant to the power of 8y plus secant to the power of 6y. All right, and then you have secant y, tangent y, dy. Now you're ready to do some u substitution. You let u be equal to secant y, so that du is equal to secant y, tangent y, dy. And this is what you've been waiting for to do all your life, because now let's keep this on one line. Don't want to waste all my lines. Ooh, I just did something stupid. Okay, so what am I doing? All right, that's what I was doing. Okay, just want all this to be in one line. And why am I concerned? It's not like I'm writing on the board or I'm writing on a piece of paper. I'm writing on a freaking iPad that has near infinite space. Okay, infinite amount of space. All right, so what do we have here? We have u to the power of 10 minus 2u to the power of 8 plus u to the power of 6. And then we have du right here, because du is secant of y, tangent of y dy is du. So we get to work, and do the integration, and this is now good. U to the power of 11 over 11 minus 2 u to the power of 9 over 9 plus u to the power of 7 over 7 plus c. Amazing, isn't it? Once you get to the easy part, it's so good. It feels so good. So this is now secant 11y over 11 minus 2 secant 9y over 9 plus secant 7y over 7 plus c. Okay, very good. All right, a little bit long, but it's locally easy. Each step is very, very easy, so it's locally handleable. We can handle it. Now, how about this? I want to show you something. We didn't talk about cosecant, but just like we talked about integrals of the form tangent mx secant to the nx, this same trick can be applied to integrals that have the form cotangent to the mx secant x to the power of n. I have to maintain one convention of pronouncing, of reading this out, right? Cotangent x to the power of m, secant x to the power of n. This same trick can be applied. So what do I mean? I mean when n is even, you factor out, oh, sorry. I meant cosecant. When n is even, you factor out a cosecant squared x and express the remaining factor in terms of cotangent of x, right? And let u be equal to cotangent of x. Same thing. And when m is odd, m is the power of cotangent, you factor out a cosecant of x, cotangent of x, and you let u be equal to cosecant, and then you use substitution. First of all, you have to write in terms of cosecant of x. So that's what we're going to do now. All right, you can pause and write this down if you want. Okay, so let's try an example. Example. What am I doing? Okay, so let's see. Let's go number three. And let's do cosecant to the power of 11th x cotangent x dx. All right, so the power of cotangent is odd, is 1. So that means we can factor out a cosecant x, cotangent x, factor out cosecant x, cotangent x dx. Save it, don't do anything to it, right? And it says rewrite every other thing in terms of cosecant, but everything remaining, the remaining thing is in terms is already in terms of cosecant. So we're good to go. Sometimes the scary things end up being easy. Sometimes scary things be easy. All right, so let's do some u substitution. Let u, why is this thick? Why is he thick? Okay, let u be equal to cosecant of x. So du dx is, if you remember from Calc 1, this is negative cosecant of x, cotangent of x, I think. And then this is dx. So we go back here. So this is u to the power of 10. And this is negative du. All right. The red part is negative du. Because du is negative cosecant of x, cotangent of x dx. Okay. So all right. So we have minus u to the power of 10 du. And this is now u to the power of 11 over 11 plus c, which is the same thing as negative 1 over 11 cosecant to the power of 11x plus c. All right. Let's try a few more. Let's look at the integral tangent to the power of 4x dx. So this is one of the ones that doesn't fall into the two cases where the power of tangent is odd or the power of secant is even. Well, we don't have a rule for this, but we know our trig identities. So we can begin by just rewriting things, like just try to rewrite things a little bit. If you rewrite this as tangent squared x, secant squared x minus 1, or tangent squared, well, let's do this. Tangent squared x, tangent squared x dx. I don't know where I'm going with this, but let's just explore it. Tangent squared x, and then we can write this as secant squared x minus 1 dx. Okay, this is getting us somewhere actually. So because we can now rewrite this as tangent squared x, secant squared x dx. You expand, and then you get two different integral. Expand and break up the integral. All right. Well, okay, let me go one by one, step by step. See what I'm about to do. Tangent squared x, secant squared x minus tangent squared x dx. So what can you do with this? You break up the integral. Tangent squared x, secant squared x, all right, minus integral tangent squared x dx. Okay, but we're still not there because the first integral is cool now because we have the power of secant is even, so we can totally handle the first integral. The second integral, power of tangent is even. We don't have any secant. So but it's quite easy to convert tangent squared x to secant and a secant actually with an even power. So we have tangent squared x, secant squared x, and then minus integral. This is secant squared x minus 1 dx. And what can we do? We can break everything up. Tangent squared x, secant squared x minus integral secant squared x, which is very easy, minus integral 1 secant squared x. Oh, I need to put my dx there. The dx's are very important, and they know they are very important because sometimes they cry if you don't treat them well. All right, so this is 1 dx. So this is quite easy to deal with now. So what I'm going to do is I'm going to let you do these integrals one by one. Or you know what? How about we do it together? Why not? Why not? One by one. The first one is quite easy. Let's look at the first integral. We're going to do them one by one. The first integral is the only one we need to worry too much about. Right? Just the first integral. So I'm going to do a u substitution that is just for the first integral. This u substitution is particularly for this first integral. I'm going to say let u be equal to tangent of x, because we factored out a secant squared. You can factor out a secant squared of x, and every other thing has been converted in naturally, automatically is in terms of tangent of x. So let's say tangent of x, so that du dx is equal to, oh, why am I doing du dx? Just do du is equal to secant squared x dx. You see that? So our integral can actually be written as the integral of u squared du, which is quite easy, times the integral of secant squared x, which we know is tangent x, plus the integral of 1 dx, which we know is just x. So this is u to the power of 3 over 3 plus tangent of x plus x plus c. But what is u? U is tangent of x over 3 plus tangent of x plus c. I think I got carried away and I putting pluses where I shouldn't be putting them. So this is negative. All right. So that's our answer to that problem. Okay. I'm going to look at one more problem, and I'm going to let you finish it. Was this number 4? So let's call this number 5. Number 5, integral secant squared x square root of tangent of x dx. So it doesn't really matter whether the power of tangent is an integer or whether it's a fraction, like in this case, as long as you have a secant squared x there, you can make, or you can factor out a secant squared x. You can go ahead and make u tangent x, particularly when the power of secant is even. So if you go ahead and say let u be equal to tangent of x, that means that our du is equal to secant squared x dx. So what do we have here? We have integral u square root of u du. That's all we have. This now becomes square root of u, and secant squared, or let's do this, let's use a different color. Secant squared dx come together to give you du. This is now easy to deal with, and I will let you do it. It's just 2 lines or 1 line actually, if you like to skip lines. I like writing things down, being very detailed. So that this is 2/3 tangent of x to the power of 3/2 plus c. That's the final answer. You should try it. Okay, so that's all I have for now. I will see you in class.